Hello, welcome to this video. So today we're going to do this problem. So for all natural numbers n, positive integers, we're not including 0, find all triplets a, b, and c. And I didn't write it here, but I should mention triplets of real numbers. So find all triplets a, b, c of real numbers, a, b, c, that satisfy these three equations. So a is b to the n plus c to the n, and similarly for b and c. So the first thing we're going to do is look at specifically the case. Let's look at specifically the case n equals 1. This is a simple case, but as we continue with the problem, we'll have to assume that n is not 1. So let's get rid of this case real quick. So a is equal to b plus c, b is equal to c plus a, c is equal to a plus b. Now notice, if I look at a plus b plus c, there are three different ways to look at it. I can take b plus c and let it be a, so that's 2a. So a plus a would be 2a. I can look at c plus a, that would be b, so b plus b is 2b. And I can look at a plus b, which is c, and make this is c plus c, which is 2c. Which means that a is equal to b, which is equal to c. We're going to just cancel the 2. Right, so I'm going to erase this because now it's not equal. So now we know these 2a is equal to b is equal to c because they're equal a plus b plus c. I'm going to cancel the 2. A is equal to b, which is equal to c. And if we plug it into just one of these equations, a is equal to a plus a, cancel a out, and we get a is equal to 0. Which means that the solution for n is equal to 1 is that this has to be 0, 0, 0. Okay. Now, for a case where n is bigger than 1, let's do a similar thing here. But instead of adding like a to both sides here, let's look at, instead of looking at a plus b plus c, let's look at a to the n plus b to the n plus c to the n. Because then I can say, I can again look at this in three different ways. B to the n plus c to the n is a. So this is a to the n plus a. And similarly, c to the n plus a to the n is b, which means that this would also be b to the n plus b. And again, a to the n plus b to the n is c, which means that I can write c to the n plus c. Okay. So now we have this equality, which means if we look at the function x to the n plus x, these three numbers a, b, and c are all at like the same height on the graph of the function. But now let's see, if n is an odd number, so if n is odd, that means that x to the n is an increasing function, right? X to the third, x to the fifth, x to the seventh, they're all increasing functions. And x is also obviously an increasing function, which means that x to the n plus x is an increasing function, since it's the sum of two increasing functions. So if this is a strictly increasing function, that means that if we have three numbers that give out the same output, then these three numbers have to be the same. So in the case where n is odd, then this function is strictly increasing, and so we have that a has to be b, which has to be c. So now let's plug in again, say to the first equation, we get a is equal to 2 times a to the n, right? So a to the n plus a to the n, which means that we can move a to the other side and take it out in brackets. We have 2 times a to the n minus 1, and this is 0. So either a is 0 which is a trivial case where a, b, and c are all 0. Or we have that this is 0. So a to the n minus 1, after adding 1 dividing by 2, it's 1/2. And remember, since n is odd, n minus 1 is even, which means that a is plus or minus 1 over 2 to the 1 over n minus 1. So this leads to a is equal to 0. This leads to a is plus or minus 1 over 2 to the 1 over n minus 1. So for this case, we have the trivial part where 0, 0, 0. The next one is when they're all plus or minus, and keep in mind it's the same plus or minus. So all of them are either all plus or all minus 2 to the 1 over n minus 1. So let's write that real quick. Second spot, and in the third spot. Okay, so that's the case now where n was odd. So now let's look at the final case. Now let's look at n is even. So in the case where n is even, I actually shouldn't have drawn a line here because I'm using a similar argument here. Okay, so we have x to the n plus x. So let's look at a function x to the n plus x. This time n is even, so it's going to be, the function is not strictly increasing. But let's look at the function. Let's check for a extremal point, like a minimal point or a maximum. So what we'll do is take the derivative. So derivative of x to the n would be n times x to the n minus 1. The derivative of x would be 1. Now we want this to equal 0. So now let's move it to the other side. X to n minus 1 is equal to negative 1 over n. Now since n is even, n minus 1 is odd, which means that there exists an x that satisfies this. X is negative 1 over n minus 1. And I don't care about the specific value of the minimum, of the external point, of this point. It'll turn out being a minimum. We'll soon explain why. But I just care that there exists only exactly one of these points, and it's a minimum because if you think about x to the n plus x, as x grows larger and larger, so as x goes to infinity, this explodes to infinity. And similarly, for x goes to negative infinity, because n is even, x to the n, it will explode to infinity. And x will explode to negative infinity, but x to the n is a stronger function and it increases faster than x, so overall, this will increase to infinity. So, in the function, if you have as it goes to infinity, as x goes to infinity, the function also goes to infinity. And similarly, for x goes to negative infinity, that means that the external point cannot be a maximum. Because it's the only external point, it's not a local one, but it's a global one. So if it's a minimum, then it's the smallest value for the entire function. And if it's a maximum, it's the biggest value for the entire function. But it obviously can be the biggest value for the entire function if it goes to infinity at both ends. Which means that this is a minimum. So the function would probably look, its graph would something like this. I don't really care. I just care there's one minimum point. And now I have 3 values that are giving me the same output for the function. But because there's only one minimum, then I know that the maximum number of different values that can give me the same output is 2. Right? You can think about it as looking at y equals some k, so y equals k, and where it intersects the function. Could that intersect above the minimum? That will be 2 points. exactly at the minimum, very unlikely but could happen, which is 1 point, and below the minimum is 0 points. The maximum would be 2. And because we have 3 values, that means that 2 of them will have to be the same. So let's just assume that these values that are the same are b and c. Now we have that b is equal to c. So let's plug it in. So let's plug this in to the first 2 equations. The third equation will give the same thing as the second equation, so we'll ignore it. And we'll get a is equal to 2 times b to the n. And b is equal to a to the n plus b to the n. And now we have what a is. Let's plug it into a plus a to the n plus b to the n. Now we have b to the n plus to the n times b to the n to the n, which will be b to the n squared. So now either b is equal to 0. In the case of b is equal to 0, then c is equal to 0, and from a is equal to 2 times b to the n, a would be 0. So we have the trivial case 0, 0, 0. In the case when b is not 0, I can cancel it out and get 2 to the n times b to the n squared minus 1 plus b to the n minus 1 minus 1. So I move this to the other side and divide it by b. This is 0. But now let's look at this as a function of b. N is even, so n squared minus 1 is odd, and n minus 1 is odd, which means that the function b to the n squared minus 1 is strictly increasing, b to the n minus 1 is strictly increasing, which means that this part is strictly increasing. Obviously, subtracting 1 is not going to change it. It's not going to change if it's increasing or decreasing. So it is increased. So this entire function is strictly increasing, meaning that there can be exactly one value where it is 0, which means that if we find a value of b where this gives 0, that means it's the only value that can give us 0. So now, inspired by 1 over 2 to the 1 over n minus 1, let's check that this exact value for b does work for this function. So let's plug in b is equal to 1 over 2 to the 1 over n minus 1. Actually, I'm not going to plug that in because it's just boring, but you can see how it will work out, right? N squared minus 1 divided by n minus 1 here will be n plus 1. 2 to the n divided by 2 to the n plus 1 is 1 half. This will just be 1 half. 1 half plus 1 half is 1. Minus 1 is 0. If you don't immediately see it, I encourage you maybe take out a piece of paper and just make sure to yourself that it's clear why this value, this specific value, does give 0 when you plug it in here. But now that we found a value that gives this function 0, we know it's the only value that gives this function, that makes this function equal 0, which means that now b and c are both equal to this. And now if I raise it to the n and multiply by 2 to get a, I get that a is equal to 2 times 1 over 2 to the n divided by n minus 1, right? So by raising it by n, I'm changing this 1 to an n, just multiplying the exponent by n. But then I have 1 over 2 to the n over n minus 1 minus 1, which gives me 1 over 2 to the 1 over n minus 1. Which means that by assuming that b is equal to c, we also got that a has to be the same value as b and c, right? This is obviously the same value. Which means that the assumption b is equal to c doesn't matter. It could have, it wouldn't have changed if we had assumed a is equal to c or a is equal to b, because these are three functions. These three equations together are symmetric with respect to a, b, and c. Which means that if we swap any two of them or any three of them in any order we want, the equations would get we would get would be equivalent to the original ones, which is pretty obvious, just from the symmetry that's going on here. And so from that symmetry, we know it doesn't matter if we would have picked b is equal to c, a is equal to c, or a is equal to b. We would have gotten the same result, that all three of them equal and are equal to this exact value, which means that the final triple we can get for this case is 1 over 2 to the 1 over n minus 1, 1 over 2 to the 1 over n minus 1, and again 1 over 2 to the 1 over n minus 1. So basically this exact triple, but just removing the plus minus. So the final solutions we got are for n is equal to 1, it's only zeros. For n bigger than 1, it's these three options. So it's this. So it's the trivial case of zeros, and plus or minus this value. And for when n is even, or when is an odd number and bigger than 1, we got this. And when it's even, we got the same thing but without the plus minus. And you can really check for yourself that in every case, the solutions that we found do actually satisfy the initial equations. And so finally, that's it. If you want more content like this, please subscribe to my channel. I'll be uploading more interesting problems and things like this in the future. And finally, that's it.